Hello, and welcome to Astronomy 100. In this video, we're going to continue our discussion of galaxies, and in particular, we're going to start to describe some of the differences between their shapes and their sizes, and some of the details that each of the shapes and sizes of the galaxies have, and how they relate to one another. Now, whenever we discuss the differences in the appearance of something, usually shape and or size, this is sometimes called morphology. So when we talk about galaxy morphology, morphology simply means the differences in the appearances of something, in this case galaxies. So when we look out in our universe, now that we know, if you remember from the previous video, now that we know that the universe is indeed one filled with many, many galaxies, we can now start to look at all the galaxies in our universe, and of course right away we start to notice different shapes and sizes. Let's go ahead and get started. In this first picture, again, our splash screen, you can again see that there are indeed different shapes of galaxies. Some of them have a bit of a spiral appearance to them. Some of them seem like just a bit of a fuzzy blob. Some of them have a bit of an irregular shape. So it becomes readily apparent that there are different shapes and sizes of galaxies. The first person to really try to make sense of this was, again, Edwin Hubble. And in 1936, using the largest telescope in the world, which at that time was the 100-inch telescope at Mount Wilson Observatory, he was locked into a research program where he was studying many of the details of the galaxies themselves. And by taking photographs and measurements of lots of examples of galaxies, Hubble was able to notice that there seems to be a classification scheme of galaxies, meaning that there were certain categories that galaxies fit into when it came to their shapes and their sizes. There are not a million different types of galaxies or a million different shapes. It turns out there's just about 4, arguably 5 different shapes. Now, after his research was published, we conveniently put it into a way to describe this, and this is often called the Hubble tuning fork diagram. It's a little esoteric, but a tuning fork has a shape to it, just like a fork you would eat with, where you have a handle and then it branches off into two branches, and that's why it's called the tuning fork diagram. Now, the reason why it's laid out this way is an organizational way to separate out the types of galaxies. In a minute, we're going to talk about each of the details of the types themselves, so we'll save those details for just a minute. But what I want you to notice is that essentially there's a type of galaxy called an elliptical galaxy, elliptical describing the shape. And of course, what you can see is that some elliptical galaxies are very close to being spherical, or if not are spherical, they're very round. And then there are other elliptical galaxies that become a little bit more football shaped, would be long and then narrow. If you could see this in 3 dimensions, it would be very much like a football. And then you can see that some of them, the elliptical galaxies, are very, very narrow, probably more cigar shaped. The numbering system has to do with the shape. So an E stands for elliptical. E0 is spherical, and then all the way to E7, which is the most elongated possible. So the bigger the number, the more elongated the type of galaxy is. The next branch are what are called spiral galaxies. The name is pretty apparent. These are spiral-shaped galaxies, and each spiral galaxy has a bright center to it with spiral arms that kind of wind away from the center. And spiral is indicated with just the letter S, and you'll notice that it's SA, SB, SC. And the way that it works is that when you go from A to B to C, you'll notice that the nucleus or the center of the galaxy is getting smaller. So SC has the smallest nucleus and SA has the largest, and you'll notice that the spiral arms are very tightly wound for an SA and very loosely wound for SC. So SA has the largest nucleus, tightest arms, and then SC has the smallest nucleus and then the loosest when it comes to the winding of its arms. Now, there is a variation on spiral that includes a bar that goes through the center of the nucleus. These are called appropriately barred spiral galaxies. It's a little confusing because it's SB, even though they're barred spirals, but you can get used to that. So SBA, SBB, SBC, and the naming of the letters and the details are the same for spirals. You'll notice that SBA is a large nucleus, tight arms, SBC is a small nucleus and loose arms. And we'll see some examples of each of these as we go. The fourth category, if you want to call it the fourth, spirals are kind of related, but let's call this the fourth category, are the irregular galaxies. And the name is really like it sounds. These are galaxies that just have no definable shape. They're just, well, very irregular. There's no central region that is uniform or arms or anything like that. And so again, the name is appropriate, the irregular. So we have elliptical galaxies, we have spiral, of course, the barred type as well, and then we have irregular galaxies. And SO galaxies are probably related to spirals. We'll talk more about those in just a minute. So let's look at some of the individual details, and we're going to go through this fairly quickly. A spiral galaxy is, of course, as the name says, spiral in shape. This example of the Sombrero galaxy is a great one. It is edge on, by the way. We're looking at almost right along its edge. But this is a SA type galaxy. Notice that it has a very, very large nucleus, and the arms of the galaxy are very, very tightly wound. And then here would be an SB, which has a smaller nucleus, and again, looser arms. M81 is the example. And then SC, a great example of this is a galaxy called M101, very, very small nucleus and very, very loose arms. Now here are some details. A spiral galaxy is usually home to quite a bit of gas and dust in the disk. Remember, the disk of the galaxy is out here, the nucleus of the galaxy is here. Lots of gas, lots of dust in the disk. Now, the nucleus is containing many, many stars. That's what actually makes it look like there's a nucleus, is there's just lots of stars here. And these stars are very, very old stars. And stars are broken down into populations, basically in the way that they are in their generations. The oldest stars in our universe are called population 2 stars. So the nucleus of a spiral galaxy tends to be very old stars. Now, out in the disk is where you find not only old stars, but very young stars. This is where there's lots of star formation occurring. Why? Because there's lots of gas, lots of dust, lots of raw material to make new stars. So lots of new stars as well as old stars in the disk, but then the nucleus is really just mostly old stars. There's not a lot of gas and dust in the nucleus itself. Now notice this interesting little fact here, that 77% of all observed galaxies are spiral. So that's kind of an interesting thing, the overwhelming majority of them. Now, of course, the barred spiral, again, very similar, but notice the very obvious bar going through the nucleus. Here's an SBA, here is an SBB. Notice the smaller nucleus, very pronounced bar. The arms, of course, are kind of loose. And then you can see here's a great example of an SBC, still barred, small nucleus, very, very loose arms. Now, elliptical galaxies, as I said, go from E0 to E7. A great example of an E0 is the galaxy M87. Again, very, very close to being spherical. If you looked at it from any direction, it would look very round. Again, vast collection of stars. And then, of course, here's an E7. Notice how very elongated it is. It's actually very much like a cigar shape, very long, round, and very narrow. And here are some details. The one thing that makes elliptical galaxies interesting is there's very little, or in some cases, no gas and dust. And if there is no gas and dust in this galaxy, that means there is no star formation. So elliptical galaxies tend to be the home of very, very old stars. Logically, if there's no material to make new stars, there are no new stars. So an elliptical galaxy is really home to very, very old stars. Notice those are population 2 stars, are the oldest stars in our universe. And these don't tend to have any rotation to them. The stars themselves individually move, but the galaxy doesn't rotate on its own. Interestingly enough, the largest galaxies in our universe are elliptical, and the smallest galaxies in our universe are also elliptical. So the largest and the smallest in our universe. Now, irregular galaxies, as promised, are, well, irregular. A good example of that is the Large Magellanic Cloud. This is the neighboring galaxy to the Milky Way. We abbreviated it as LMC. Notice the shape really is just kind of irregular. There is no central region. There are no arms. It is just truly a very irregular shaped galaxy. M82 is another good example of an irregular galaxy. And what we know is that these are sort of the opposites of elliptical galaxies. Irregular galaxies are home to lots and lots of gas and dust. And of course, if you have lots of gas and dust, you're going to have lots of stars forming where there is plenty of material. So irregular galaxies have the most star formation occurring of any type of galaxy. Lots and lots of stars forming at any given time inside of an irregular galaxy. And of course, if you have lots of stars forming, you're going to have lots of very young stars. Of course, some stars stick around for a while, so you have some old stars as well. Now, interestingly enough, irregular galaxies are frequently found near other galaxies, and it could be that the shape, the irregular shape, is caused by interactions. One galaxy running into or through another galaxy can destroy the shape and create just sort of a chaotic irregular shape. So it could be that interactions are causing this. Now, in the Large Magellanic Cloud, there's something very interesting. This right here, we're going to zoom in and make it this picture here. This is a nebula, a cloud in the Large Magellanic Cloud, this galaxy, that is home to one of the most prodigious star-forming regions that we know of any galaxy. I'll zoom in. This is R136, a very boring name to this cluster, but this cluster in this cloud, in this galaxy, has some of the most brightest, hottest, youngest stars in highest numbers in quantity that we know of. There are more O and B type stars in this cluster than we know of any other galaxy. So what that is saying is that there's a tremendous amount of star formation occurring in this cloud called the Tarantula Nebula. I love the name of that. And the star formation is the result of lots and lots of gas and dust mixed with gravity. You're going to get lots of star formation. So it is a cloud that has a big cluster of very, very young stars. Of course, these are the hottest, biggest, and most luminous stars in our universe. Now, the last one I want to tell you about, these are called SO. That's not a zero, it's SO. And these are called lenticular galaxies. And these are still not quite understood that well. Sometimes these are referred to as armless spiral galaxies. They have some of the features of a spiral galaxy, but they don't seem to have the arms. And here are three examples that you can see here. And of course, these have some features that start to suggest that they are similar to spiral galaxies. But they have some of the hallmarks of elliptical galaxies. They have very little gas and dust, like an elliptical galaxy. There is, of course, no recent star formation. And you can see that there's some strange shapes, and as you can see in this bullet point here, it's very complicated to try to subdivide this into a separate category. Now, interestingly enough, these are the most common galaxies found in very, very crowded, high density means crowded, clusters. So it is believed that maybe this particular shape or this morphology has to do with interactions. When one galaxy gets close to another galaxy, the gravity can distort the shape and maybe wipe away the arms or cause its shape to change based on that interaction. So galaxy morphology is still one of the cutting edge areas of astronomy. There's still much to learn about galaxies. And what we start to know nowadays is that it could be that the shapes themselves are something that changes over time. That perhaps you start with a galaxy that has an elliptical shape, but then computer simulations show that two elliptical galaxies that gravitationally pass by and interact with each other can start and create the formation of spiral arms. So it could be that a galaxy's shape today is not the shape it has always been, but that shape has been molded through collisions, interactions, and clusters. And it's just widely believed now that the shapes of galaxies that a galaxy has is something that would just simply change over time. A lot to learn about galaxies. Again, there are many astronomers working on the shapes and sizes of galaxies and what we can learn from that. It's an interesting area, but keep in mind the tuning fork diagram when it comes to the basic shapes and sizes and of course all the details of the galaxies. Now, in our last video that we'll get to after this one is we're going to talk about sort of the big, large structure of the universe itself. What is the big picture? What would the universe look like if we could see it on a grand scale? We're just about out of time, so I hope you join me then.